Master the structural architecture of data by exploring how memory layout defines software performance. Welcome back to our series on data structures. Today, we tackle how elements are physically or logically arranged in memory, starting with linear models. Computer memory is inherently a linear sequence of addresses. However, our programs often need to model multidimensional or hierarchical real-world systems. Linear data structures organize elements in a sequential fashion. Every single element has a unequal predecessor and successor except for the very first and last. Classic examples include arrays, linked lists, stacks, and queues. They process items in a strict order, perfect for chronological feeds or task scheduling.
Nonlinear data structures abandon simple sequences. Elements connect in hierarchical or interconnected networks representing complex relationships like organizational charts or maps.
Trees represent parent-child relationships without sepals, while graphs model unrestricted networks like social connections and global routing paths.
Now let us shift dimensions to memory. Allocation static data structures have a fixed size determined that compile time allocating exact blocks of memory upfront.
Static structures offer incredible access speed and memory safety because pointers are predictable. However, they waste space if oversized or overflow if data exceeds limits. Dynamic data structures grow and shrink. During runtime, they request memory from the heap as needed, adapting fluidly to changing program workloads. While dynamic structures solve capacity constraints, they introduce overhead garbage collection. Pointer differencing and memory fragmentation require careful engineering.
Let's examine how these dimensions intersect. A structure can be both linear and static, like a fixed size array, or nonlinear and dynamic, like a growing graph.
Fixed size audio streaming buffers rely on static linear arrays to ensure zero allocation. Jitter during real-time playback speed is paramount. Conversely, social networks use dynamic, nonlinear graph databases to instantly update millions of user connections and friend recommendations. Assessing elements in layers. Static structures takes constant all-time traversing. Nonlinear dynamic trees takes logarithmic or linear time, depending on balance.
Static structures have zero-pointer overhead. Dynamic structures store extra reference pointers alongside every data, not increasing total memory consumption.
Choosing the wrong structure type cripples algorithm efficiency. Running pathfinding algorithms on linear static arrays instead of graphs would be computationally disastrous.
Modern hardware architectures with multi-level cache hierarchies heavily favor contiguous linear memory layouts due to cache locality principles.
Software engineering has evolved from rigid memory mapping to highly abstracted dynamic structures managed automatically by modern runtime engines. Engineers must analyze read frequency, write frequency, and size predictability before selecting between linear, nonlinear, static, or dynamic models.